Okay, hello everyone. I'm Paul Drabble, Marketing Manager with Delta Q Technologies, part of the Zappi group of companies. I'd like to welcome you for day 2 of the Future of Electrification virtual conference, and thank you for tuning in to this session topic, Specialized Electric Motor Solutions Powering the Future. Just so you're aware, this session is being recorded, so it's available to watch on demand for your convenience in the future. Questions are great. If you have any, go ahead and add them to the Q&A tab in the top right of your session window, and they'll be discussed at the end of the session. Note that your questions will be posted privately. With that, it's my pleasure to introduce Björn Berweiler, who is a development engineer at Schabmüller, who are part of the Zappi group of companies based in Germany. Björn, I'll pass it over to you to tell us about Schabmüller and to begin your presentation. Thank you.
Okay, thank you, Paul. Yeah, welcome from my side. Good afternoon, everyone, and welcome to my presentation. My name is Björn Berweiler, and as already mentioned, I'm development engineer specialized in permanent magnet motor at Schabmüller. Schabmüller has a long tradition or history in producing and developing electric machines for motors, starting in the early 60s with DC motors. We now offer a wide range of different motors, DC, asynchronous machines, permanent magnet machines with continuous power output up to 200 kilowatts. Schabmüller machines find application in many applications like material handling, agriculture, construction machines, buses, trucks, driverless transport systems, and many other applications. In today's presentation, the focus is on permanent magnet machines, especially regarding the NVH and torque ripple problem. So first of all, I want to start with the situation. The situation is we have several synchronous machines. So seen right now, the TSS 150. So to get things clear, TSS stands for synchronous machines in-house, and 150 marks out the size of the machine. So it's the outer diameter of the electromagnetic active part. It is an interior permanent magnet machine with neodymium ferrite bore magnets. If you're a customer, you can purchase it as air or water cooled version in the voltage range from 48 to 96 volts, or as a high voltage machine from 350 volts to 720 volts. The limitation is 7,000 RPM, or this is for the air cooled version, and for the water cooled version, it's going to be like 10,000 RPM, and the machine is capable of producing output up to 70 Newton meters. Further on, we have a TSS 170. It's a slightly different approach. It is a spoke design with ferrite magnets. It's so far only available as an air-cooled machine for low voltage applications. It is limited to 4,200 RPM and 110 Newton meters. Our most powerful machine is the TSS 214. It is also an IPM machine with neodymium ferrite bore magnets. You can get it as an air, water, or oil-cooled machine. It is available as low voltage or even as high voltage machine. The limits are 12,000 RPM for the oil-cooled machine, and it can produce torque up to 740 Newton meter. So that's the situation. What's the complication about all these machines? If you have magnets in the machine, you can produce high power densities, which might lead to torque ripple and also to noise and vibration problems. On this plot, I've brought to you, this is just an example. It's the cogging torque of the TSS 240. So it's like no load applied to the machine. If you would spin it with your hands, you could, if you have a pretty precise measurement device, you could measure this torque curve. So seeing this plot, you can see it has a torque ripple from peak to peak with 6 Newton meters. And when we're looking to a load point, this is just random load point, we will look at the same later on, but you can see we have on the right side now the torque per mechanical angle. It has an average torque of 245 Newton meters, and the delta is 14.8% from peak to peak. So this is quite high values for synchronous machines, and from our customer perspective, there might be high requirements for NVH. So that means the torque ripple needs to be reduced. But for sure, our customers do not want to pay anything additional for this feature. And from our side, so from the manufacturer side, we are looking for cost-effective solutions that are suitable for our serial productions we already implemented at our site. So ideally, no extra cost, no extra processes or tools. So this is the agenda for today. I already talked about the situation and the complication. Further on, I will talk about the object of investigation, so the particular machine we're looking at. I will talk about measures for torque ripple reduction. I will introduce to you the step skewing under restriction of fixed segment length, and afterwards, finishing, I will sum up and show the solution. So, talking about the object of investigation, today we are looking at the TSS 240, as already mentioned former slides. It is like this one shown on the slide. It's the water-cooled version of this machine. On the bottom, you can see the simulation model we are using to calculate performance characteristics and other stuff. So what we're looking at is a permanent magnet machine with the stator, where the stator is a straight stator, so nothing turned or something like that. It's not skewed. The stator is laser welded on the outside, and it has a distributed winding. The rotor is a V-shaped. The rotor with buried magnets in V-shape. The rotor surface itself is flower shaped, and the cookies each are 30 millimeters. So this is something common to our synchronous machines. We produce machines, or we receive cookies, and we can produce machines in step size of the cookie length. So for the TSS 240, we can increase the active length of the machine from 30 to up to 300 millimeter. And on the right side, you can see one of the TSS 240 rotor cookies. The speed range, as already mentioned, is up to 12,000 RPM. The rotary thrust is up to 70 kilonewton per square meter. This is the continuous value, so axial length 30 to 300 millimeter. And yeah, it's on series production, so we have tools available for punching, winding preparation, and insertion. So talking about this and talking about the complication I investigated early on, we do not want to change anything on these points. But when you look at measures for torque ripple reduction, the first thing, or one thing you can find, is when looking at the stator, it is short pitching. So this is something that affects the winding. So on the right side, we can see two different cross sections of the TSS 240, and on the upper version, you can see that both winding layers are shifted against each other. This is something which would effectively reduce the load torque ripple. This would do nothing to the cogging torque, but the load torque would be reduced by this. Yeah, exactly. And so, yeah, cross section remains the same, but the problem is there are two phases in one slot if we would opt for short pitching. That would mean that we need a separator between upper layer and bottom layer, because we have two different voltage levels within one slot. This would also increase the complexity of the insertion process and reduce for sure the effective slot area, which would also lead to higher ohmic losses, so less efficiency. The other measurement you can find when doing some research is skewing on the stator side. This would mean you can remain the actual winding scheme of like single layer winding, but you will have to investigate new processes, because you will have to insert the winding into the loose not packetized laminations. Afterwards, you will twist the sheets or the laminations of the stator, and then have to weld it or packetize it in any way. So this is something which would result in a completely new process at Schabmüller, and this is why we do not want to opt for it. So we have talked about the stator. On the next slide, I want to talk about the rotor. So what are the measures for torque ripple reduction on the rotor side? The first one is skewing. This is something commonly known from asynchronous or induction machines. But we're looking to permanent magnet machines, it becomes a little bit tricky, because skewing on the rotor side, you rotate, or you rotate each lamination against the former one, and you can not work with buried magnets. Only if you have a 3D printed rotor, then you can print your pocket for the permanent magnet into the rotor itself, and then you can work with buried magnets. But 3D printed rotors is nothing really nice for serial production. So the other solution for reducing the torque ripple and or cogging is a step skewing. So this is like we have the cookies, and we twist the cookies against each other. That would relate to reduction of torque ripple, but it is depending on the number of segments or cookies available for the active length, and the number of segments depends also on the cookie length divided by the actual length, or the actual length divided by the cookie length. Okay. The next point is step skewing under restriction of fixed segment lengths. This is what I already tried to figure out a little bit. So we have, for the TSS214, rotor cookies of 30 millimeter length. If we are looking for example on a machine with 210 millimeters axial length, this would result in 7 segments of each 30 millimeter long. So for this presentation, I will only focus on 3 step segmentation. That means that we are looking to 3 different segments with individual number of rotor cookies, but only 3 different angles along the transversal of the machine. So looking at this, we will look at some different variants of this. So the status quo is a straight rotor. On the top right, you can see it's 7 cookies of 30 millimeter, each aligned in the same angle. The second version we're looking at is the unbalanced but symmetric distribution. So we have 2 cookies at slightly rotated towards the rotating axis, 3 segments aligned with the rotating axis, and 2 segments a little bit in delay regarding the 3 segments. On the other hand, we are looking at an unbalanced, unsymmetric version. So there we have two cookies, and then 3 cookies. And as a comparison, like for optimal results, we are looking at a simulation model which has evenly distributed segment lengths. So this is something we could not realize in a Schabmüller when looking to 210 millimeter active length. But if we're looking at 90 millimeter active length, then we could do just 1, 2, and 3 cookies, each of them rotated slightly. Okay, so but when we do this, what's the outcome of it? So how does it influence the cogging? Is it sufficient to reduce cogging and or the torque ripple? And what other effects does it have? So after presenting the segmentation versus axle length problem, I want to talk about the results on the cogging torque. So on the left side, this is the simulation or optimal version, which is not producible from our side. But if we are looking at the simulation results, in the background or with the light blue color, you can see the straight rotor, which has, as already shown on slide 2, 6 Newton meter peak-to-peak value for cogging torque. And if we are applying this stepped skewing with evenly distributed segments to the rotor, we can nearly eliminate the cogging torque completely. So we can see like 0.2 Newton meter peak-to-peak torque for this version. If we're looking to the unbalanced but symmetric version, it looks like the plot on the right side. We do not reach the exact same reduction of cogging torque, but it shows that it's also pretty good or capable of reducing the cogging torque to below 1 Newton meter for this kind of machine. To not bother you with several plots and different curves, I've prepared a sum up. So we're looking at this table on the top left. It says we have the reference version. Let me just get out the laser pointer. We have the reference version. This is the 210 millimeter without any skewing or step skewing. It has a 6 Newton meter ripple. And we are comparing this one to the 3 versions below. So for the one slotted step skewing, we can see 3.3 and 15% of the 6 Newton meter peak-to-peak torque are still available. So it is obvious that it's a pretty good approach to receive lower cogging torque. For those of you who have not been in touch with skewing or staggering, step skewing, the angle from the first to the last segment of such an rotor construction is called the staggering angle or skewing angle, and this is mainly limited to 1 slot width or 2 slot. So in the simulation model, I can easily adjust 1 to 2 slots, and this is why we're also looking at the 2 slot version on this side. And you can see that 1 or 2 slot does not affect the results for cogging torque. In general, we can see that peak-to-peak torque is decreased effectively by step skewing, but it does not do any change if we skew about 1 slot or about 2 slots. So what about below point? To show you or to give you an indication or a feeling of what we are talking about, I brought to you the efficiency map of the machine we are talking about. So this is the efficiency map of the TSS2 14-210 millimeter length. It reaches torque up to way over 400, slightly below 500 Newton meters, up to 10,000 RPM. And we are looking to the rated point, which is mostly like the highest efficiency point at 5,500 RPM and at almost 240 Newton meters. So for this point, this is the plot you already see on the second slide. This is the torque ripple under load for this distinct point. So for the 200 and it says 245. This is just because some simulation related after post-processing stuff. It is the same point, but this plot is neglecting losses. But it says 14.8% torque ripple. If we're looking to the symmetric, not realizable segmentation, so the optimum result we could receive if we are going to step skew with 3 steps, this is the result. So we can reduce the torque ripple from 14.8% to 3.8% by remaining the same average torque. If we're looking to the symmetric unbalanced version, we see almost the same result. So the output is, or the torque ripple is reduced to 4.5% of the actual not skewed version. As already showed for the cogging, we also want to look at some overview or summarize and not go over lots of curves and plots. As already known from the cogging slide, we refer to the unskewed version of calculation results and compare the 3 skewed versions. Also for 1-slotted and 2-slot skewing. And on the first table, we look at stator current demand, because when applying skewing, that means that the effective torque we can produce by the same current is going to be lower. To retrieve or to achieve the same torque, we have to increase the stator current. And this is what it looks like when we skew for the angle of 1 slot. The current increases on all 3 versions around about 2%. If we skew for 2 slots, it's obvious. So the misalignment, as you can call it, is higher, and therefore the current demand also is higher compared to the 1-slotted version. Next, we want to look at the effectiveness. So what is the outcome of this measurement? The torque ripple by skewing along 1 slot is reduced to 3.8 to 4.5%, and if we go to 2-slot skewing, it is reduced to 1.4 or 2.8%, related to the 239.2 Newton meter, which was the requested torque. So what we can also see within this result is that we can shift the results to what we want or what is the customer request. So if the customer request is almost like we are not able to spend more current for certain points, we would definitely opt for the 1-slot version. So if the customer has special demands on current and or reducing the torque ripple, you can opt for unbalanced or balanced version. So this is right now I will come to the summary and or solution. So step skewing, as we've seen within the results, is a valid approach for reducing both cogging and the torque ripple. Unbalanced segmentation decreases effectiveness, but can be adapted to achieve individual demands. It is applicable for sure for all our synchronous machines, TSS 150, 170, and 240. It is applicable with existing series productions. It's just an alignment question during the process of rotor assembly. And it is a suitable solution for customers with high demands for NVH without increase in cost. Thank you for your attention. Are there any questions?
Okay, thank you, Björn. Dankeschön. I'm just looking at the QA tab, and I'm looking. The Q&A section is sort of rolling, but I'm not seeing any questions, unfortunately. But it could be a technical issue. But if you do have a question and the Q&A tab doesn't seem to be working, you can just put it in the chat, in the session chat. Maybe wait a minute or so, but it doesn't look like the Q&A tab is functioning there. So just a little. It seems to be loading, but I don't see any content coming up there. In any case, if the Q&A tab doesn't seem to want to work today, you can email your questions to Björn. The contact information for Björn is on the screen there. His email address and phone number. I'm not sure the Q&A tab is working today, Björn. So I think. Oh, actually, no. I see 2 questions have come up, but I can't see them. Okay, not sure why I can't see the actual questions that have come up, but okay. Well, there a question came up in the session chat. The TSS 150 and the TSS 214. Are they series production motors?
Yes, absolutely. Everything I've shown today is on series production. So TSS 150. 170 and 240 are all 3 of them are in series production.
Okay. Yes. So okay. Yes. So the Q&A tab's still not working, but if you do have a question, please post it in just the session chat, not the Q&A section. So. Okay. Right, now there's 5 questions I can see that are stacked up. I just can't read them.
Maybe I can have a look.
Okay, perhaps can you see them? Yes, okay, I do. I'm getting the information from another channel. So one of them is, what about whole-back array in order to reduce the cogging torque in comparison to skewing? That sounds like a good question.
Yeah, it's a good question, but it's slightly out of what we were looking at. So, as mentioned in the beginning, we were looking to processes we already have, processes and especially cross sections we already have in series production. So we do not want to change anything on the geometry, material, process, tooling, etc. So, yeah, Halbach arrays might be a valid solution if you develop new products. You can look at these ones. There are many other technical difficulties by going to these kind of machines, but for our approach, and especially for value for money for our customers, we opted for this one, for the step skewing.
Okay, hope that answers that question. Another question: do you see IPM rotor design being the best solution?
Yes, so far it's pretty capable of high speeds. I mean, there are different point of views when looking to high speed, but for our applications, from traction drive or for pump to traction drives, the demanded speed is up to 12,000 RPM, 10, 12,000 RPM, and this is where I absolutely see the IPM machine as pretty favorable.
Okay. Next question: can you briefly discuss the importance of lamination alignment accuracy?
Regarding what? Is the question.
Okay, I'm reading a question here.
in radio, in
Sorry,
actual and tangential, there are several directions to discuss. But when talking about the step skewing, each segment should be aligned pretty well. If we shift the segments not on the exact angle, effectiveness will be reduced in any point. If we go too far with the angle, the torque will decrease more, or the current will rise even more. If we go too less or too small angles regarding the optimum, we would not achieve the same amount of torque ripple reduction. So it would be a good solution to find the perfect angle and apply it to the rotor topology.
Okay. Another question: does SRI PM motor reduce torque ripple?
So what's the question?
So if you go to the chat session, does SRI PM motor reduce torque ripple?
I'm still in the Q&A. So SR.
Okay, yes.
What is SR IPM? Maybe Mathieu Terras.
Okay, Mathieu, you posed that question. If you could just, if you're listening, if you could just clarify that question you've posted on the session chat.
Synchronous reluctance.
Okay.
If we're talking about synchronous reluctance, it absolutely depends on what kind of rotor elimination. So what's the design of your rotor elimination? What's the cross section of the machine? Synchronous reluctance machine. He wrote it, synchronous reluctance motor. Always suffer from the demand of reaching high LD LQ values or ratios, not values. So this is why you are opting for the least amount of material towards the air gap, which will lead to, like, from perspective of the air gap, it looks like the rotor is slotted, and this would lead to interaction between rotor and stator. But this is like the physical stuff behind torque ripple or cogging in that case, and it might reduce torque ripple for sure, but it absolutely depends on the geometry. I'm sure, Mathieu, that does not
answer. Did you see Mathieu did clarify that he was talking about synchronous reluctance motor with permanent magnets?
Yeah, I think this is not what Mathieu wanted to hear, but if you do not know the exact geometry, you cannot say that it's better or worse than IPM.
Okay. Any more questions there to feed into the chat session? We still have just under 25 minutes left, so here's your chance to ask the expert here. Okay, looks like all right. We have one more question. How do you minimize magnet strength variation from affecting torque ripple?
I'm not sure if I understand the question correct. Minimize magnet strength.
Okay.
So we do not affect the magnet strength itself. I mean, yeah, in flux weakening mode, we sort of apply contrainductive field towards the rotor, which might have influence to the magnet strength, field weakening. But the torque ripple effects you see are variation from manufacturer. Okay. Yeah, this is like supply quality question, not sort of production and simulation related stuff. You have to ensure that you have good quality checks that magnets you buy from supplier are constant in quality. Hope that answers these questions.
Okay. Any other questions for Björn? Okay. Well, last chance to dance, as I say. If not, we will end the session. Thank you, everyone, for participating in Björn's session here. As you can see, his contact details presented on the slide there. Feel free to reach out to Björn if you have any further questions, or reach out to Schabmüller. But thank you, everyone, and don't forget that our keynote speaker, Alex Edmonds, is presenting in just over 20 minutes, presenting a case on electrification. So I would highly recommend everybody tune in to that content. So thanks very much, everyone. Once again, Björn, thanks for presenting, and Dankeschön and guten Abend. And we will see you soon.
See you soon. Bye-bye. Thanks, everyone.
Okay. Bye-bye, everyone. Okay. Thank you.